All right, so let's see. We need the antiderivative of sine of x plus 1. Antiderivative of sine is negative cosine. Remember, the derivative of sine is cosine. The others are the negatives. So the antiderivative of sine is negative cosine. And the antiderivative of 1, for any constant, you reattach the variable. That's what this variable indicator is for, to let us know which variable we're reattaching. Now, you will notice, now the previous example I just kind of glossed over it. You notice I'm not putting plus c. Now, the official explanation for that is we are free, by the fundamental theorem of calculus, we are free to choose any antiderivative we like. And so I chose, we are free to choose the one where c is equal to 0. But some students don't like that until they see what's actually happening. They actually observe what happens to this constant of integration. So what I'm going to do this time is I'm going to go ahead and put in plus c, and you're going to watch what happens, and you'll see that whatever constant I choose, it turns out it really doesn't matter. It doesn't matter, and it'll become intuitive here in just a moment. So for now, I'm going to put the constant of integration in plus c, and then watch what happens to that. So this is evaluated from 0 to pi over 2. All right. So what I'm going to do is put evaluate at the top. Evaluate at the top minus evaluate at the bottom. So evaluate this at pi over 2. So pi over 2 goes in for all the x's. So I have negative cosine of pi over 2 plus pi over 2 plus c, whatever it is. And then I have minus negative, be very careful, negative cosine of 0 plus 0 plus c again. And you're thinking, oh, that's what happens with it. I figure out what's going on here. Well, so let's see if we can trace this the rest of the way out. So we know cosine of pi over 2 is 0. So this is 0 plus c minus, we know cosine of 0 is 1, and we want the negative of that. So that's negative 1 plus 0 plus c. But now what happens when you distribute this negative? That becomes plus, that becomes minus. So we end up with pi over 2 plus c plus 1 minus c, and the constant of integration cancels anyway. So that's why we don't even need to write it. Yes, it's true, it will cancel anyway, but more to the point, we're free to choose the constant to be anything we like. We choose it to be 0. The fundamental theorem gives us the freedom to choose c to be anything. So when we choose it to be 0, we don't even need to keep track of it. And so the net result is pi over 2 plus 1. Notice that a definite integral, your answer is a number. On the previous example, it was whatever it was, negative 9 or something, whatever it was. The definite integral is a number. An indefinite integral, if this were an indefinite integral, there's two things. Indefinite integral, you do need the constant of integration. Indefinite integral, this problem is done right here. There are no limits of integration, and you do need the plus the constant. And then indefinite integral, your answer is a function. Definite integral, you do have limits of integration. You don't need the constant of integration, and your final result is a numeric value. So that's how you compute definite integrals. Find any antiderivative you like, typically choose c to be 0. Find the antiderivative, evaluate at the top minus evaluate at the bottom. And that's a consequence of the first part of the fundamental theorem of calculus. Now what I'll do next is talk through what does that have to do with the Riemann sum, and does that all make sense?